Space Center. I'm Michael here in my home for another edition of Ask an Astronomer with our astronomer, Rachel Wang. Hey, Rachel, how's it going?
It's going well, but it's getting really cold outside.
It sure is. That's why we're all bundled up here. I've
Mhm.
got my house coat nearby warming up my feet. How are you keeping warm over there?
I've got a heated blanket on my lap right now, actually.
Well, hopefully all of you are keeping warm at home. We've got a really packed show with a lot of fun space stories to go over. So if you have any questions about any of the stories that we're going to go over, put them into the chat. We will also put some links into the description of this YouTube at the end as well. And we're going to be going over a bunch of different stories. But of course, if you have any questions about the universe, we'll go over those over the next 30 minutes. So to start us off, we actually have an event next week about gravitational waves, Rachel, but this was kind of a coincidence because we had planned it before, and then there was another big discovery from LIGO, the observatory that has detected more gravitational waves. So Rachel, why don't you tell us about this, our big story, our big lead story about gravitational waves this week?
For sure. So I'm just going to share my screen. You should be able to see a slide that says new detections and then a nice little diagram showing how many detections they've had so far. And what's really interesting is if you take a look on the right, it's the cumulative count for each of their observing runs. And so the most recent run was from April 1st to October 1st of 2019, and that's this purple part over here. But what you'll notice is that they had a massive spike in detection. So that's what we're all really excited about, because in their previous two observing runs, the total number of events that they detected was only 11 events, and they detected 39 more in just that small period. So that's incredible how they were able to up their detections by that much. And now the particularly interesting thing is, and what I actually learned a couple of days ago, was how they increase the number of detections. And they use this really fancy term called quantum squeezing. And so what that is that it talks about the fundamental fuzziness of quantum mechanics, and that we can't really know things for certain because quantum mechanics is this probabilistic theory of our world. And so with quantum mechanics, they have this thing called the Heisenberg uncertainty principle. And what that says is that if you have two variables like position and momentum or energy and time that are linked, that we can't know one and the other with infinite precision. So if we measure one, then we'll have much more uncertainty in the other one. So what they did is they actually exploited and abused this principle. So how they did that is they purposely increased the uncertainty in one respect. And you can see that here on the left. You can see that if you look towards the Y being projected on this side here, that it's really, really wide. So that means it has a lot of uncertainty. But that also means that if you look at it from the other direction, that uncertainty is a lot smaller, a lot thinner. And so that's exactly what they did to get these increased number of detections. I thought was really cool that they were able to use this quantum mechanical fact to their advantage to be able to up their sensitivity. And so I thought this was kind of cute that they had a really nice video showing 38 of their binary black hole detections as they're merging together.
Okay, so we need to back up here a minute, Rachel, because if you're out there and you're watching this and you're like, what are we talking about here? We're talking about gravitational waves, and of course, we're going to be diving into this deep next Thursday evening at Cosmic Nights, but gravitational waves were theorized by Albert Einstein way back in the day. Finally, was confirmed a few years ago by this observatory. Well, I say in quotes observatory because it's not an observatory like we have at our space center with optical mirrors. We're talking about these lasers that you're showing here on your screen here that are detecting just these minor fluctuations, right, Rachel?
Yeah, and when we say minor fluctuations, we're talking about differences in length of 1/10,000th the width of the size of an atom. So it's incredibly sensitive. And whenever I think about LIGO being this laser interferometry gravitational observatory, it's just an incredible feat of engineering how they were able to make these 4-kilometer long arms being able to detect that such a tiny difference in distance. It's crazy.
Yeah. So next Thursday evening, we're going to be talking with Jess McIver, who works out of UBC at the Gravitational Waves group. That sounds like a really fun party, the Gravitational Waves group. But they also work directly with LIGO. And as a bonus interview, I have found actually the lead operator at LIGO. His name is Corey Gray, and he's going to be taking us on a little bit of a tour of this observatory. And one of the questions that I'm going to have for him is, how they're able to distinguish gravitational waves, like two black holes, like colliding with each other, with just maybe other random vibrations that are happening, perhaps on the street, like a big truck rolling by. Like there was a truck that just rolled by my window just a few minutes ago and everything rattled. So these are some of the questions that we're going to dive into with Corey Gray, but this is actually really, really amazing. And so what's like the big picture here, Rachel? Like, we're looking at a bunch of new detections. We're looking at a bunch of black hole mergers, right? Yep. So what is this really telling us about what's going on in the universe?
So, of course, like with any kind of sort of science experiment, you want more data. And so having this wide variety in all these different kinds of mergers, especially with black hole mergers, is particularly interesting. And we had a brief moment of time where we only had these two kind of species of mergers, and that was black hole mergers and neutron star mergers. And then eventually we ended up finding a nice little mixture and having a black hole and neutron star merger. So having that wide variety over different kinds of objects coalescing and eventually merging, and also different masses as well, as we saw in this lovely little video showing all the different kinds of black holes merging together. But it's really just showing the diversity and allowing us to peer into what these gravitational waves look like and what's causing them.
Really fun. All right. So if you want to get in on the action next Thursday night, Cosmic Nights, we're going to be in Zoom. Your ticket is going to get in there. You're going to be with me and Rachel and Dr. McIver. We're going to have some fun stuff. We're going to have even a few games that we're going to play as well. So make sure to get your ticket for that. Okay. The next story, Rachel, I was actually really excited about because we're talking about one of my favorite places in the solar system, and that is Jupiter's moon, Europa. Now, the reason that Jupiter's moon, Europa, is one of my favorite places is that it has more water on it than is on the Earth, which means that there is a pretty good potential. I mean, I don't know what like the percentage of how you're going to rate it, but a fairly decent percentage that there may be life down there in that ocean. And this new picture came out from actually isn't a picture. It's actually an amalgamation of what they believe the dark side of Europa looks like. Why don't you explain this picture to us, Rachel?
Sure. So I have a little screenshot of the tweet from the Jet Propulsion Laboratory here. And I just had to point out their caption that says "Ice, Ice, Baby." I quite love that. But it's kind of funny that you're saying that, this is really an ocean world, because if you take a look at the bottom, it doesn't really look like it is. It looks kind of like this icy surface, maybe somewhere you'd go to take your family for a ski trip or something like that. But the interesting part about this is that they found that Europa glows, but they knew that Europa glowed before. But this is a slightly different glow than the glow that they saw before. And what made it slightly different is the composition of the salts that were theorized to be on the surface. And so they knew that there was magnesium sulfate, which is basically Epsom salt, and sodium chloride, which is table salt. And when they accounted for this in their recreation of the environment of Europa, they found that when Europa is being bombarded with high energy radiation, that it actually gives off a glow. And this glow is a little bit different than the glow that we see from our moon, because our moon has this white fine dust called regolith that reflects the sun's light. But with Europa, it's not quite that reflection that we're seeing here, because it's actually glowing in the dark. And so that's what we mean by the dark side of Europa is glowing. That's because of this high energy radiation interacting with different kinds of salts.
This is really fascinating to me, because I'm now imagining, if somebody was living on Jupiter, and just like how we look up and see our moon, would they look up and see this glowing Europa up there?
Well, it depends on what wavelength you have for eyes.
Yeah, really fascinating. And of course, Europa is going to stay in the news probably for the next decade or two, because NASA is sending a mission towards it, right?
Exactly. Yeah. So we have the Europa Clipper mission. And even though the Europa Clipper mission isn't exactly a life-finding mission, it'll be interesting to have it takes a little bit more data on this phenomenon, taking data on the composition using spectroscopy. And what's also really interesting is that this is one of those weird kind of scientific, predictions that they came from knowing what the composition was and then making that prediction rather than going to the place, sampling, and then coming back and then kind of hypothesizing what went on. So they actually already know, and now they're going to make sure that they can confirm what they are theorizing. So I thought that was really, really cool, kind of a backwards way of approaching this kind of science extrapolation.
Well, I mean, that's kind of how science works. You know, you make some theories, and then you go there and you try to discover them, which is exactly what Einstein did with gravitational waves, right?
Exactly.
And the Europa Clipper mission, I think, is really important because we haven't really gotten any close-up views of Europa in a while. Now, Juno is a spacecraft that is still orbiting around Jupiter, and occasionally it does take some pictures, but its primary mission is really to take pictures of Jupiter. We really haven't gotten many good pictures of Europa, I think, since Voyager, right?
Yeah, and you know, it's kind of difficult because we can see Europa from Earth. We see them as one of the 4 Galilean satellites, and you know, we're discovering new things about moons all the time. You know, with our moon, we found some new stuff recently, and also with even Saturn. You know, we had those 20 new moons or semi-recent new moons that were discovered just looking at archival data. So we're constantly learning more and more about moons.
Yeah. Now, before we leave Jupiter, I do have to point out for anyone that is outside. I know here in Vancouver, it's been raining. It's pretty much been raining all week, but Jupiter is up there in the sky. And if you wanted to look at it through a telescope, you might actually see Europa, right, Rachel?
Yeah. And actually, that was my first experience at the Gordon Southern Observatory, looking through the telescope there. And that was looking at the Galilean satellites through our telescope. And that was really cool, being able to see them all lined up in a plane around Jupiter.
Awesome. And we actually are going to be opening up our planetarium and our observatory into December. So make sure to check our website for those dates because that is going to be really exciting. We got lots of planets out there to look for. Can't wait. Okay, let's go on to our next story, which is kind of an old story, but we're gonna come back around to talking about OSIRIS-REx, which was the big news story a couple weeks ago. It's now on its way back to Earth, but we've got an update on the mission.
Yeah, so what's really cool is that they managed to store the sample. And what that means is that when they took pictures using the TAGSAM camera, which is attached to the sampling arm, they saw that they were actually losing a little bit of sample out into space. And so now that they've stored the sample properly in this capsule that's going to be delivered, dropped off to Earth in 2023, somewhere in the Utah desert, now they've confirmed that they have secured that sample and they're not losing or actively losing debris to space. And they actually managed to secure around 60 grams worth of asteroid material. So I'm really excited to see when they examine that, what they're going to find.
So they almost got like too much material, right?
Yeah, well, I mean, you know, the more the better, but yeah, it is heavy to bring all that stuff back as well.
Well, that must have been like incredibly exciting because, there was, a small, chance that if they didn't get enough material that they were prepared to go back down for another tag event. And so they kind of go through these checks. And I find it really fascinating, when we're doing these remote missions, you don't have like immediate confirmation. Okay, did the mission work? And they have all of these checks set up to make sure that, okay, if it doesn't work, then they have a backup plan.
Exactly. And especially with that light delay time, with communication. So that's why the OSIRIS-REx mission had to be completely autonomous, because there was no way that they could communicate fast enough to tell the robot how to fix whatever it was doing wrong. And what's interesting is if they did actually fail to collect the sample, or they didn't collect enough, or whatever happened or whatever went wrong, they wouldn't actually sample the same site. So they had 4 sites picked out. And because if they failed sampling this site that they did, they would have disturbed the surface already. So if they were to fail and they wanted to retry taking another sample, they would go to another site. So that's a whole other, site to align to, and then make sure you're sampling correctly. And it's a whole other thing. So I'm glad that they got it first try.
Absolutely. So OSIRIS-REx is coming back to Earth, and when should we be expecting it?
So it'll arrive in 2023. So OSIRIS-REx will just drop off the capsule and it'll go through our atmosphere. And then it's supposedly going to land somewhere in the Utah desert.
Okay, hopefully away from anyone living there. And us asteroid return missions are going to be still in the news. So in a couple weeks, the Japanese Space Agency is going to be bringing their probe, which did have an encounter with an asteroid that does have a bit of an asteroid sample with it on Hayabusa 2, and that is going to be returning to Earth at the beginning of December.
Yeah, which is kind of really nice that we had all these. It almost feels like it's perfectly timed, like we're getting the Hayabusa sample now, and then hopefully that'll help inform us.
Oh, did you freeze there, Rachel? Rachel may have frozen, but I'm gonna keep on going here. So if anyone has any questions about anything that we're talking about asteroid return missions. We're talking about what we can see up there in space. Looks like we lost her. Rachel's going to come back. Let's see. We got Pride on the live chat. Hey, Pride. Table for One. Thanks, Pride. Thanks Table for One for checking this out. And Clive. We recently regained contact with Voyager 2. Would you like to see a new Voyager-like mission in the future with a collection of cultural images attached to the probe, like a new era golden record? There you are, Rachel. I knew you were coming back. I had faith. Did you catch me reading out that Clive's question?
I caught
read it out again?
Very last part. So yes, I would love to.
So yeah, Clive is talking about Voyager 2 mission, which I was talking about, took those pictures of Europa. Would you like to see another type mission in the future that has a new era of a golden record?
Yes, I would. And even though I say yes, I would be a little nervous about it because, Voyager 1 and Voyager 2 had a lot of just kind of crazy things go wrong, but then they manage to fix themselves somehow. And I think that one of the best stories is actually their actuator getting caught and getting stuck. And they found that this would happen after like a few hundred uses of the actuator. And what that meant was when Voyager was flying by these planets, these gas giants, which we hadn't seen for the first time, it was looking in the wrong direction. It was looking out into space and completely missing everything that was behind it. And then they managed, with some clever engineering and some clever code, they managed to fix the actuator and ended up getting Voyager pointed at the gas giants as it was flying by. But, I would hope that now that we sent Voyager 1 and Voyager 2 and they're well on their way to the interstellar space, that if we were to do another similar mission, that things like that wouldn't happen.
Well, I think that's a good testament to, any of us that are working on things, going through challenges. Sometimes when you are faced with those big challenges, you learn so much. And even though in the moment it feels like, the end of the world and like you've worked so hard for these moments, but the problem is actually exciting. And actually read recently to learn to love the problem and not the solution. So kind of like try to like really get excited about, the challenges that you're working on rather than focused on, eventually what you're going to get in the future, because, you don't know what innovative ideas you're going to come up with to fix that solution. And that really could be the thing that is groundbreaking.
Yeah, that's a really good point because, we didn't know the impact of the images that Voyager collected, what that was going to have on our planet and for the public perception of space travel. And especially with Carl Sagan convincing NASA to turn the probe around and take a picture of our pale blue dot. And Michael, I see that you have pale blue dot right behind you. But, having the picture of our Earth as that dot caught in the sunbeam is absolutely incredible. Like it gives you more of that overview effect than you would have seeing the Earth from space. It really shows us how almost small and insignificant we are.
Yeah. Well, I did put those books back there on purpose, Rachel, because a few days ago, Monday was Carl Sagan Day. So I do want to give a shout out to one of my favorite science communicators. Did you do anything to celebrate Carl Sagan Day on Monday?
Not in particular, but I did read a few chapters out of the book, actually.
Awesome. A question coming in from Faith, a really good one here. Why is it dark in space when there are so many stars?
Oh, that's a great question. And that has to do in part with when you have starlight, it decreases quite quickly as you go up with increasing radius or increasing distance away from your star. And then we kind of see that same thing happening with sound waves, right? So when you have sound waves, because you can imagine sound waves almost like ripples coming out from a pond, the further away you are, the more it decreases, and it decreases with your distance away squared. And kind of the same thing happens with stars as well. But you're also thinking about the fact that space is so immense, and for you to detect light and to see light, you need photons to be hitting either your eyeballs or the surface of something to be able to see that light. So if we had more stars, maybe if we had, maybe 10 or 15 billion times more, then we would have a lot more light. But because everything is so far away, it's so spread out, we get that darkness of space.
Yeah. And even though there are billions and billions, to quote Carl Sagan, even though he didn't actually say billions and billions, but even though there are billions of stars out there, space is even more bigger than all of those stars combined. It's hard to wrap your head around just how much space there is.
Exactly. Yeah. And I like to throw back to the fact that I first learned in my first year astronomy class, which is if you imagine the grains of sand on a beach and all the tiny little grains of sand, we have more stars in our universe than there are grains of sand covering all the beaches here on Earth. So it's just unimaginably huge. And space is just so, so empty. In the places that you don't have anything, what we call cosmic voids, you have an average density of around 1 hydrogen atom per cubic meter. So it's incredibly empty. But there is stuff going on. There's stuff like in the quantum mechanical world, there's virtual particles popping in and out of existence. There's little fluctuations in energy. So in that sense, it's not quite empty, but to us, it looks like this terrifying black void.
Yeah, absolutely. Sometimes it is terrifying, although I find it intriguing. I like, not knowing what's out there. It's kind of like you can be scared of what's under the bed, or you can look and find out. It could be something exciting. It could be something you lost that you've been looking for.
Well, I always get this feeling of, I imagine myself doing EVA on the ISS because that's just, what I dream about in my spare time. But I imagine when they go on EVAs and they look below their feet, nothing is it's just emptiness. It just gives way to these stars in the backdrop. And me being extremely terrified of heights, I can't even imagine what that would feel like as an astronaut, having to focus on your mission, but also, dealing with this deep fear that there's nothing surrounding you. And the only thing that's tying you to humanity is this tether.
Yeah, actually, I was just listening to Tim Peake, who was an astronaut with ESA, and he was talking about when he was doing an EVA, and he said he had been trained, not to look down, which he said is such an uncontrollable urge, because why would you not want to look down? And so of course he did look down, and for a brief second was completely in awe because he saw Australia down there, but then immediately regretted it because he just got completely overwhelmed with vertigo and was like, no, I can't look down there.
Oh gosh.
Another question coming in, how far have humans ever gone into space? Talking about the ISS and talking about Voyager. What are we talking about here?
Yeah, so we haven't quite yet shuttled people off into deep space, somewhere like Mars. We have for rovers, but with people, we've generally stuck around in this low Earth orbit. So, the ISS is in low Earth orbit. It's around 400 kilometers up in space and altitude. But before we can start shuttling people off to places like the moon or places like Mars, we need to make sure that we have the proper technology and that we've practiced it again and again and again. And that's why we're sending more rovers to Mars first. Like Perseverance is on its way there. I think it's well over halfway. I think 56% of the way there to Mars currently. But besides our local system, the Earth and the moon, we haven't quite yet sent people a little bit further beyond that.
Yeah. But at some point, NASA says that they will be sending humans back to the moon with the Artemis mission. So in the next few years, we'll hopefully be seeing that. Question coming in from Pride, who comments on my bookshelf. It's just an IKEA bookshelf. It's not a fancy bookshelf, Pride. Or maybe that's what you're saying. You're making fun of my IKEA bookshelf. But she asks about the temperature in space increasing. Is that right?
Ooh, that's an interesting question. So what I would say is I'm thinking that it'd actually be the opposite, that it'd be decreasing. And I'm thinking about this on a longer time scale than, the entire existence of humans, on an astronomical time scale. And specifically, I'm thinking about the time scale of the universe. So we have a conjecture, which is our leading hypothesis for what's going to happen to the end, or what the ultimate fate of our universe. And that is something called the heat death of the universe. And it sounds terrifying, I know. But really what that's saying is that we know that the temperature of the cosmic microwave background is around 2.73 Kelvin. And with absolute zero being 0 Kelvin, that's the coldest of the cold, where you get, almost everything on the atomic level and beyond being frozen in place, almost like that. And so with the heat death of the universe, we're saying that, well, we know that our universe is expanding. And not only that, it's accelerating in its expansion. So it's getting faster and faster and bigger all the time. And because of this, then we're thinking that, okay, well, if we're expanding something that's so large, if you imagine even having a box of gas and you expand it, it'll get colder. And so the same thing is going to happen with our universe, and to the point where, it'll expand so much and so vastly that the distances between things, distances between galaxies, between stars, will be so much that light won't be able to travel fast enough to traverse that distance. So eventually we will have super extremely dark skies, darker than we have right now. So in theory, our universe, or this cosmic microwave background as we see it now, should be tending towards 0 Kelvin as the universe continues its expansion.
Okay, so make sure you got your spacesuit on if you're leaving Earth, or we can stay on Earth and we can fix some of our problems with climate change. We can have a nice time here. Maybe staying on Earth is the way to go. Another question coming in from something spacey, great name, talking about the James Webb Telescope, this telescope that we've been waiting for. So when the James Webb Telescope does get launched, will it be able to create the beautiful pictures like Hubble does?
And before I dive into that, there's a good joke about the James Webb Space Telescope, which is we don't know what's going to come first, if James Webb is going to go up or the heat death is going to come first. And I love that joke because it's been delayed for so long.
Yeah.
But yeah, so James Webb is going to act as a successor to Hubble. And Hubble Space Telescope was really important because it was primarily looking at visible light, and it gave us these wonderful pictures that really helped with the public perception of space science. And so James Webb will do something similar. So it will be able to give us those pictures, but it's going to be primarily looking in the infrared or the near infrared range of light. And the reason that it's doing this is because we have a lot of interstellar gas and dust between us, or where the James Webb Space Telescope is going to be, and everything that we want to see that's really far away. And so with James Webb, with having this infrared capability, it can actually see right through this dust, unlike a visible observatory like Hubble, which would be blocked by a little bit of that dust. Being in the near infrared, you can see right through it. And that's really important because of the concept of look back time. So telescopes look back time tells us the further away we look at something, the further back in time we're looking. And that's because of the finite speed limit of light, which is kind of crazy to think about.
Yeah.
But yeah, so with James Webb, we're really looking to see if we can see further back in time to where, these solar systems are forming and the beginnings of galaxies, and just really seeing the furthest that we've ever seen before into our past.
Amazing. Yeah. So it really kind of has to shift our perspective, because Hubble really did give us this really pretty pictures into the universe. And James Webb will be doing that, but in a different kind of a way. It's like a time machine. And that is incredibly exciting to be able to look back in time. They should have called it the DeLorean, maybe.
You should name the future telescopes.
One final question from Faith. In the future, would it be possible for humans to land on a gas giant?
Ooh. So I don't want to rule it out because I am a sci-fi nerd. So I really don't want to say no. I don't know how they would do it, but it'd be really cool. But the problem with gas giants right now is that they have extremely high temperatures and pressures, and they don't have a solid surface. And that's why we saw Cassini do that deep dive and get disintegrated in all of the stuff that's floating around Saturn. And so that would make it a little bit difficult. But if we could figure out a way to land on some sort of surface, or gaseous surface of a gas giant, that'd be really interesting for us to take sample data and try to sample the interiors of gas giants, because that's really difficult for us to do right now.
Yeah. Before we send you off, I just wanted to share our website, because we got a whole bunch of really fun activities coming up. So next week, for any home learners out there, we've got a whole session. Rachel, I think you're leading this one, right?
Yes.
So it's the universe. So this is grade 6 and grade 10 science curriculum aimed for ages kids 12 to 16 years old. This is going to be on November the 17th, 10:30 to 11:30. You can go onto our website. We've got a whole session. You'll be in with Zoom with Rachel. It's a guaranteed really fun time. And like I had mentioned before, Cosmic Nights, which is our deep dive. I'll go to a little bit higher into our educational knowledge. But if you're still wanting to just learn the beginnings of gravitational waves, still going to be really fun. We're going to be in Zoom as well with Dr. Jess McIver, assistant physics professor from UBC. And of course, for any teachers out there, I see that there was a class joining here, Division A3. CL Chen's class. You can go over here, you can go into learn, you can go into program guide and bookings for teachers and parents. And we've got a whole host of online programs for teachers. Of course, right now, everyone is online right now. We have transferred all of our school programming online. So make sure to go onto our website, check out what we offer. And of course, here for our bi-weekly Ask an Astronomer. I know, Rachel, you're going to be away in 2 weeks again, but I will find a suitable replacement. I know that 2 weeks ago, I found Joanna Wagstaff, and she was really honored to be stepping into your shoes. She says that she hopes she did a good job. But in 2 weeks, we will be back here on YouTube for another Ask an Astronomer. So make sure to like and subscribe. You'll get your notifications for when we go live again. Thank you so much for tuning in and watching. Stay safe. We'll see you again next